So with today's lecture, we're going to take the concepts that we learned in solution chemistry and in equilibrium and apply them more specifically to solutions that are acids and bases. So to do that, we're going to identify essentially what an acid and base is. What are the different definitions? There's multiple definitions. We're going to focus on two. And then we're going to give examples of where we can find acids and bases. And we're also going to name some of the acids and bases to help us identify which ones are strong and weak and what is the difference in their characteristics. So there are several definitions for acids and bases, and we've slowly been exploring these definitions. We did when we went in chapter 6 with chemical reactions, and we were discussing double displacement reactions, one of the double displacements being neutralizations. So what definition you use really depends on what you're studying. Okay, so one definition we won't discuss is Lewis acid and base, because that's really popular in organic chemistry where there's not a lot of water, but we're focusing on water. So we deal with equilibriums and solutions in water. So our definitions are going to be slightly different than that. So we'll cover the most common ones. So an acid is a substance that essentially produces protons. So we've discussed this in the past. The hydrogen ion essentially is a proton. The reason why it's a proton is the hydrogen atom has a proton in its nucleus and one electron. If you lose an electron, all that's left in the hydrogen is a proton. So a lot of times the hydrogen ion is referred to as a proton. So an acid is anything that releases a proton in water. A base is anything that will basically dissociate and produce a hydroxide ion. So this is how a base can be defined, something that produces a hydroxide ion. We saw this when we did the neutralization reactions, the double displacement, where I wrote, you can generically write out the acid as HA and the base as BOH. And then in the double displacement, right, we're switching partners. We're doing kind of a do-si-do here. And we end up getting water, which I had you write as HOH to help you balance it, and the salt. So we've seen this definition, and this is your Arrhenius definition. This is the most common, the simplest of all definitions, is looking at something and just saying, oh, there's a hydrogen that can be produced in water, it's an acid. There's a hydroxide, it's a base. It is by far the simplest, and it's the one that we've already seen. So again, these are restricted to water solutions, and that's okay because that's what we're primarily dealing with. So an example of an Arrhenius acid is, I could take hydrochloric or hydrogen chloride gas, throw it in water, and it dissociates 100%. So it'll break apart to give me these protons and a chloride ion, and it will be 100% dissociation. So it will completely break apart, giving me if I have 1 mole of hydrogen chloride gas, it'll give me 1 mole of protons and 1 mole of chloride ions. So one of the things you want to realize are acids are actually electrolytes, because electrolytes are essentially a solution that has ions, and the ions allow for conductance of electricity in solution. The other thing that you want to know about acids is they have a sour taste, right? So citric acid is an example of an acid found in citrus. If you had litmus paper, they would turn the litmus red. They also neutralize bases. So these are things, turning litmus, we've worked with litmus paper, we've done neutralization reactions, and we've talked about the dissociation of acids and electrolytes. So here are 2 examples. we have nitric acid, and they actually draw the Lewis dot structure for you, which is really nice. And if you look at the nitric acid, what they're omitting is the lone pairs. So really this would have your lone pairs there, and your lone pairs, so that everything has an octet. But this is nitric acid. It is essentially a nitrate that has an extra hydrogen attached to it. This is my acetic acid, right? So my lone pairs would be there, my lone pairs would be there. So these are two examples of acids. And what makes them acidic is that right here in this bond, there's 2 electrons. And when I throw this in water, the oxygen steals the hydrogen's electron, and I end up getting an H+ ion, and then the nitrate group is left over. And the electron that the nitrate stole would be right there. And that's where the extra, negative charge from NO3- comes from. So nitrate, right, is derived from nitric acid. Once it steals that hydrogen's electron and releases a hydrogen ion in solution, it's behaving as an acid. So with acetic acid, it doesn't do it as well. And that's where we actually get, instead of one-sided arrow. So when you have nitric acid and you throw it in water, you'll see a one-sided arrow. And the reason why you see a one-sided arrow is this is a strong acid. And dissociates 100%. If you throw acetic acid, it's a weak acid. So what you see is the double arrow because it's in a state of equilibrium. And it will produce, and this is why they write it as CH3COO- sometimes. It'll produce the acetate ion, which we've written out in the past as CTH3O2-, and a proton. And that electron that I circled right there is the one, whoops, it's actually in this bond, that the oxygen stole from that hydrogen. So why do we have to kind of revisit some of the nomenclature? Well, look at all the different acids. And I didn't really require you guys to know any of these, oxy-acids. If you look back, I didn't really require you to know any of those oxy-acids because when I was going over nomenclature, people were getting, a little overwhelmed. But we did visit the binary acids, like hydrochloric and hydrobromic. And I did talk about acetic acid. But now you're starting to notice, well, wait a second, there's all these other acids I need to know. So one of the things is it might be nice to review some nomenclature. Okay. So how can I do that? Well, that'll be pretty straightforward. I can go back. Whoops, sorry about that. And you guys might remember one of the things that we first talked about, we talked about binary ionic, binary covalent, and then we talked about binary acids. Does anyone remember what a binary acid is? What did binary stand for?
Two.
Two. So to be an acid, right, we just learned acids do what? You need to be able to release a proton, and then you had a non-metal. And we learned this. This is good review for the final, right? We learned HCl, HBr, HI, and then, down here I'll put HF. So this would be hydrochloric acid. So what does this, how do we distinguish that this is binary? It has the hydro prefix and the ic acid suffix, right? So what would this be called?
I think your screen is frozen. Are you writing anything?
I am writing. You guys don't see it?
I don't see it
I only
online.
see the PowerPoint.
Yeah, I only see the PowerPoint.
Oh, really?
Mm-hmm. Yeah, it's just showing the naming some common acids, like you're not zoomed in on it.
Okay, let me try that again. I'm sorry. Thank you for letting me know. I didn't even realize that.
You're welcome.
Can you see that now?
Yes.
Thank you for letting me know that. I'm sorry.
You're okay.
So binary acids, as you guys stated, binary means two. I have a proton and a non-metal. The name is derived, the root, from the non-metal. So HCl is hydrochloric acid, right? So we use the hydro prefix and the ic acid suffix, and we use a non-metal's root to name it. So for this example right here, what would that be called?
Hydrobromic acid.
Hydrobromic. Excellent, Andrew. So this is good review because we need to know this. This would be hydrobromic. What would this be?
Hydroiodic.
Excellent. Hydroiodic. And all three of these binary, these are three of the six strong. So these are three of the six strong acids. And you need to know all six, okay? So these are three of the six. Now this binary is hydrofluoric, but it's a weak acid, okay? So this is reviewing the binary acids, all right? Now, what I didn't require you to know in the past was the oxy-acids. Right, so your oxy-acids are basically hydrogen, oxygen, and a non-metal. Right? So one example is the one that I had in the PowerPoint. I had nitric acid. Do you guys remember that in the PowerPoint?
Yes.
So nitric acid, you may remember that we did go over the 5 big eights. Do you guys remember the 5 big eights I told you to know? Right? Nitrate, carbonate, phosphate, sulfate, chlorate. Well, this is why I told you to make sure you know that, because the ic acid is derived from the 8 ion. So if I take nitrate, which is NO3 minus, and I add 2 hydrogens to it, that's nitric acid. Now, why is that important? Well, okay, let's see if we remember this one. Does anyone remember what that is?
Sulfate.
Yes, that is sulfate. So see how there's 2 negative? What does that mean? How many H pluses do you think I can add to that?
2.
2. So guess what H2SO4 is?
Sulfuric acid.
Excellent. It's sulfuric acid. So what I'm trying to show you is the 8 ion gives me the ic acid. The 8 ion gives me the ic acid. Now you need to be careful because this is sulfuric acid, but you may remember, what was H2S called? Does anyone remember that? Is it an oxy-acid or is it binary?
It's
H2S.
Binary.
It's binary. So what rules do we use for binary? We use what? Hydro prefix ic acid. So this would be hydro sulfuric acid. So you don't have that hydro prefix in sulfuric acid. Why? It's not binary. It's an oxyacid. And oxyacids names are derived from the oxyanions that we went over. Remember the 5 big 8s? Well, now you know why I told you to know those, because you need to know them for chapter 10. So nitric acid, sulfuric acid, okay? Oh, it's not going to give me, let me go down. I need an extra page here. So if I go down a little more, right? Does anyone remember the name of that 8 ion?
Carbonate.
I'm sorry? What was that, Sam?
Carbonate.
Yes, that's carbonate. So carbonate, what kind? It's got a 2 negative. So how many hydrogens could I attach to that?
2.
2. So what do you think the name of H2CO3 is? Is that hydrocarbonic acid?
No.
No. Why doesn't it have the hydro prefix? It's not binary. There's more than 2 elements. It's an oxyacid. So the oxyacids, what do? They take the 8 ion and they simply add the ic acid suffix. They do not have a hydro prefix. So what would I name this acid right here, this oxyacid?
Carbonic acid.
Yeah.
Exact carbonic acid. So why is this good review? Well, you have to know those 5 big 8s I told you to be able to name the ic acids. So we've done, let's see, we've done nitrate sulfate review to get nitric sulfuric acid. I just did carbonate and carbonic acid. Are there any other 8s that I should know?
Phosphate.
Yes. Okay, and what's the formula for phosphate, Andrew? We could use that 4. Remember the 4?
Right. Is it PO3? No, PO4.
Is it? It's PO4 because it's on the freaking 4. And what's the charge?
3 minus.
Yes. So what do you think? So if this is phosphate, okay, this is my phosphate ion. What do you think phosphoric acid would be?
H3PO4.
Excellent. H3PO4. And why 3? Because phosphate has a 3 negative charge. So do you guys see why it made you really needed to know those 5 big 8s because everything kind of built on that? Do you guys remember? I remember that was a long day because, 6-hour days are long days when you're learning, but that's one of the main reasons I emphasize that. So there's another 8 that we're not remembering. Does anyone remember what that, or that we haven't finished? Does anyone remember the last big out of the 5 8s I told you to know?
Chlorate.
Excellent. And that was what? Cl. Does it have 3 or 4 oxygen?
3.
It has 3 because it's not on that freaking 4, right? So there's 3 and it has a negative charge. This is chlorate. Excellent. You're doing great. So chlorate. So what would chloric acid be?
HClO.
HClO. Am
3.
I done? Not HClO, because chlorate, remember the ic acids derive from the 8 ion. So what does chlorate have? How many O's?
3.
So chloric acid has to have what?
3 hydrogen.
No, the
Oh.
hydrogen comes from the charge, not from the number of oxygen.
Oh, so 3 oxygen also.
Oh yeah, 3. I'm sorry, I thought you said 3 hydrogen. Right? So we're using, you know, the 8 ion to give me the ic acid, but the charge is what gives me the number of hydrogens. So you can look at all of those, right? So the 8 ion, carbonate has 3 oxygens, so carbonic acid has 3, but the charge is what gives me the number of hydrogens. Does that make sense?
Yes.
Yes?
Yep, makes sense.
So now I got to get my PowerPoint. Sorry about that. Why does it say stop share? Your screen share is paused. Okay, so can you guys, you probably can't see my screen, can you? Can you see my screen, or
We still
Yes.
see the Word document.
you still see the Word document? Okay, let me get, all right. So let me go back to where we were. Let me stop share, new share. Just gonna share my entire screen. It's better that way. It's a little clunkier. So you might remember we were just talking about nitric acid. So again, the ic acid was derived from what? The 8 ion. So this is nitrate. Why is it 3? Well, because it's not on the 4. Remember that trick. So nitric acid, nitrate. Why is there only 1 hydrogen? Well, because there's only a -1 charge, right? And they write the hydrogen in front to let you know that this is an acid. Now, with acetic acid, if I remove this hydrogen, right, what's left? C2H3O2 minus. Why is it only -1? Because there's only 1 hydrogen. Right? And this would be the acetate ion. So if you look at all these, what do we see? Hydrochloric acid, that's the binary acid. Hydrobromic, remember I said this was a unique one, hydrocyanic. Here we have the acetic acid that I talked about. And then if we look at our big 8s, here's nitric, right? Here's sulfuric, here's carbonic, phosphoric, and then chloric. So those were all the acids that I just went over on that Word document. But all of these ic acids that are oxy-acids were derived from the 8 ions: nitrate, sulfate, carbonate, phosphate, and chlorate. But are there other acids on top of the binary and the oxy-ic acids? Are there additional acids? Are there more acids?
Yes.
How come? Well, remember, instead of nitrate or sulfate, I could have what? The ites. You guys remember the ites? You're probably like, oh, Sean. But how were the ites different than the 8s? What did the ite mean?
It only had
It's
3.
less than.
It had one less oxygen,
Oxygen.
right? So nitrate has 3, nitrite has 1. Sulfate has 4 oxygens, so sulfite has 3. Chlorate has 3, so chlorite has 2. So we learned that. Now, I didn't require you to know it because at that time it was kind of overwhelming, I guess. But now we're at the point where, okay, well, now you have to be able to recognize that the ites are 1 less. That's why I was telling you, make sure you know those 8s because now we need to know that the ites are one less. And why is that? Well, now the ates give me the ic acid, but the ites give me the us acids, like lus, one less. So the nitrite ion gives me the nitrous acid. The sulfide ion gives me the sulfurous acid. The chloride ion gives me the chlorous acid. Now with chlorine, what do we notice? We can have more than just one less oxygen. We could have what? Two less. Do you remember us talking about this?
Yes.
If you have two less, not only do you have the ite suffix, but you also have another prefix. Now you have the hypo. So this acid here is not just the chlorous acid, it's the hypochlorous, because it's two less oxygen from the chloric. So all those rules, and we can revisit those, I'll revisit